After introducing the concepts of least squares estimation, followed by weighted least squares estimation, we now introduce a third estimation procedure, BLUE, or Best Linear Unbiased Estimation. Let's have a look again at our results for least squares estimation. We found the expression for the unweighted, or ordinary least squares estimate, x hat. It is only dependent on the design matrix A. If we would insert a unit matrix, I, in this equation, we find that this unweighted estimate is in fact a special case of the weighted least squares estimate, where a weight matrix W is introduced that gives some observations more importance or weight than others. With these equations, we now have the basic elements to obtain an estimate for x, given a specific set of observations y. However, this set of equations does not give us a clue on how to find the optimal weight matrix W. It seems rather subjective to insert particular values in this matrix. We're going to discuss this issue in the context of BLUE, Best Linear Unbiased Estimation. But first, let's recap the weighted least squares estimation solution. We formulated our y is ax problem and came to the least squares estimate x hat. Essentially, what we did was to minimize the differences between our actual measurements, which are the red crosses here, and the linear model that we assume to be applicable, which is the green dashed line. But we did this by giving some observations more weight than others, as expressed in the weight matrix W. In the plot, the observations with a bigger cross represent observations with more weight. The differences, or residuals, are indicated by the little vertical blue lines, and we call these the least squares estimates of the residuals, or E hat. Mathematically, we obtained this solution by minimizing the weighted sum of the squared residuals, which then yields the weighted least squares estimate. So far, we have considered the least squares estimates in this video. However, from our introduction to the concept of estimators, we know that if we consider the observable vector y, which is stochastic, then also the output is stochastic. Thus, we obtain the least squares and weighted least squares estimators instead of estimates. Best linear unbiased estimation is another method for parameter estimation, with a different historical background and based on different concepts. But it is also remarkably consistent with the other forms of estimation we just discussed. The underlying concept of BLUE is to find a linear estimator which is unbiased, and it is the best one among all other linear unbiased estimators. Here, the word best means that it has the best precision, or in other words, its dispersion or variance is smallest. Now, in this video, we could derive the BLUE estimator step by step, going through tedious derivations and arriving at the corresponding equations at the end of a very long video. However, I would rather spoil the story for you and tell you directly how it ends. Here you see the final appearance of the best linear and unbiased estimator x at the bottom, in comparison to the weighted least squares estimator at the top. Do you see the similarity and the difference? The form of the equation is identical, but there's an important difference. Instead of the arbitrary weight matrix W, BLUE uses one specific weight matrix, which is the inverse of the covariance matrix QY. Remember that the covariance matrix holds information on the quality of the observations. This makes sense, since we want to make sure that high-quality observations have a greater weight to the final estimate. And similarly, low-quality observations should have a lower weight. To be complete, the similarity in the equations also holds for the y hat, which can be elaborated further, and the E hat, which is elaborated in this way. Now, there are a lot of equations on this slide, which may seem difficult if we present them in this way. But remember that a large part of this just follows from filling in the expressions. We could take this part away again and have a final look at the result. Thus, the main thing to remember from this introduction is that blue uses the quality of the observations as an input to optimizing the estimation. This quality is stored in the covariance matrix of the observations. To summarize, here we see the three different forms of parameter estimation. The ordinary or unweighted least squares method, the weighted least squares method, and best linear unbiased estimation, or blue. If you take some time to grasp the essence of the equations, you could classify them in different ways. For example, you can regard blue and unweighted least squares as special cases of the weighted least squares. Have a look. The unweighted least square solution is the same as the weighted least square solution with unit weights. And blue is the situation in which the weight matrix is the inverse of the covariance matrix of the observations. But we could also classify them in a deterministic class and a probabilistic class. This distinction is only for the underlying principle, since obviously the resulting estimators are all stochastic, if we consider the random vector of observables. The reason that ordinary and weighted least squares are deterministic principles is that their solution does not use any information on the stochastic properties of the observables. The blue principle, on the other hand, is stochastic, as its solution is derived from the requirement that the estimator should be unbiased and optimal in terms of precision, as we will see in the next video. Therefore, we need the statistical expectation and dispersion of the observable vector. So, in this video we introduced best linear unbiased estimation, not via some kind of mathematical derivation, but by simply stating the final set of equations. I would like to encourage you to memorize this expression for blue. In my view, it is one of the most valuable equations in engineering, with a very wide range of applications.